have that points A 3, 4, as you can see 3, 4 for point A, B 9, 6, 9, 6, and point C 11, 2 are shown on the following diagram. Okay, alongside the perpendicular bisectors of AB, AC, and BC. So the first thing I have to go over before I jump into part A, B, and C is for us to understand what the heck is a perpendicular bisector. So straight to the point, let's understand that it's two words. It's perpendicular and bisector. In what context does the word perpendicular arise? Perpendicular arises when we talk about slopes. So when we talk about slopes, you either have the first version, or the most common, which is parallel slopes, and then the second version, which is perpendicular slopes. Okay, these are the special sort of slopes you can encounter. And the parallel slopes, how do they look like? It is two lines that are like right next to each other, and they never stop increasing, and also they never touch each other. And why do they never touch each other? They never touch each other because they grow at the same rate. And so if they grow at the same rate, they are never ever going to touch each other. But if they were just a little bit different, even by just a tiny little bit, something like this, you can immediately see, oh, okay, they're very similar, but one of them is growing a little bit faster than the other. And so eventually, if you extend these lines a lot, you will find that they actually do touch each other eventually. And in this poorly drawn example, you notice that they touch over here, because in the example that I just drew, their slopes are a little bit different. For parallel lines, it is very important that we understand that parallel slopes are equal to each other. So the slope of one, I use M for slope. See, M for gradient, slope, whatever. Slope is the same as gradient. So parallel lines means that the slope of the first one, M1, has to equal the slope of the second one, M2. On the other hand, for perpendicular slopes, the fancy math sort of like equation is that the first one times the slope of the second one has to equal -1. And commonly how people remember this is really that the slope of one, if it's perpendicular to the other, means that it's going to be negative the reciprocal of the other one. See? So oftentimes we talk about, I don't know, you have a slope of 3 or 4, and this is the slope of your first line, and you know that it's perpendicular to the second one. So that means that if the slope of your first one is 3 over 4, the slope of your second one is -4/3. How does it look like? It looks a little bit like this. Ka-ching, ka-ching, boom, 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 right? So it's two lines that cross each other in such a way that you actually end up with a bunch of 90-degree angles, okay? So perpendicular lines look a little bit like that, while parallel lines look a little bit like this. So for us to understand this thing about perpendicular bisectors, we can immediately, let's only focus on one example. See, let's immediately focus on AB. That it? So the perpendicular bisector of AB, and I'll explain why, the perpendicular bisector of AB is this one right here. Okay, this is perpendicular bisector of AB. And it's perpendicular because, as you can see, if I were to draw a line between A and B, I end up with the 90-degree angles. And this is also a hint. If I have the slope of one of them, I can find the slope of the other one. So that's already a big hint that I'm showing you right off the start of the video, ¿cierto? And the other thing we need to understand is that, okay, so it's perpendicular, but what is this bisector thing? What's happening, ¿cierto? Guys, bisector. Bisexual, bi is for two. And sect, it's kind of like you're cutting something. See, so bisect, when you dissect a frog, for example, in science class. Actually, back in the day, I dissected a cow heart. It was kind of crazy. Point is, a bisector is something that cuts something in two. And so, how is this a perpendicular bisector? It's perpendicular because, well, it's perpendicular lines. There's 90 degrees in the middle. This has to be true as well, ¿cierto? And also because it is bisecting. If this distance here that I'm putting now in red, ¿cierto? If this distance, I'm going to make it up, see? If this distance from here to here is 3, then that means that the distance from here to here also has to be 3. That's why it's a perpendicular bisector, okay? Those distances are the same. That is the intuition of a perpendicular bisector, and the main way I think that you end up using this is because you identify the word perpendicular, and this immediately allows you to use these formulas here, ¿cierto? That the slope of one is equal to the slope of the other one times a negative and reciprocal, ¿cierto? I know that this formula is a little bit crazy, so what I suggest is that you actually memorize or learn a couple of examples. So for example, if these are perpendicular, 3 over 4, the slope of the other one has to be negative 4 over 3. If the slope of one is, I don't know, 1/2, then if the other one is perpendicular, it has to be negative 2 over 1, which is the same as just leaving it as negative 2, ¿cierto? Anyways, that is what's happening, okay? So now we can jump into the action. Now we're ready to face this problem, because immediately you can say that, again, they tell us the perpendicular bisector of what? Of BC. So which one is the perpendicular bisector of BC? Well, between BC, it's got to be this line here, ¿cierto? So that perpendicular bisector intercepts the axis at coordinates 0, -1, which makes sense because we're talking about this point there, and 2, 0, which is this point here, ¿cierto? Also makes sense. Okay, for part A, we need to write down the equation of the perpendicular bisector of BC. So I'm just going to jump like straight into it, you guys. For part A, we need to write down the equation, ¿cierto? But the like hidden thing here is that you need to write down the equation of what? Of the perpendicular bisector. Yeah, but in its essence, you're writing down the equation of a straight line. And in the formula booklet, if you go ahead and open it, and well, I don't have it with me right now, but you will discover that within the formula booklet, if you go to the part of straight lines and etc., and I've shown this in other videos, and I know you can check it out yourself, you will encounter what we call the point slope formula, or point slope form, I'm not sure, see? And this equation, for me at least, it's the only relevant one. See, the point slope formula is absolutely essential for creating lines. Okay, I know the other ones can also help you create lines, but for creating lines, I highly suggest you learn the point slope formula at its heart. How does the point slope formula look like? It looks like this. Y minus y1 equals m parentheses x minus x1. All you really need to fill in is what I'm putting now in yellow. y1, x1, and m. What the heck is x1, y1? x1, y1 is quite literally just a point, a set of coordinates. While m, as I introduced a little bit earlier, it's a slope. So what did this guy online just tell you? This guy online just told you that for you to create a straight line, all you really need is a point and a slope, and the knowledge that you have to plug that in to the point slope formula. So for the perpendicular bisector of BC, they already give me 2 points, 0, -1 and 2, 0. I'm going to go with 2, 0 because why not keep things positive? Mindset and perspective is your life at the end of the day, see? So I will be choosing 2, 0. ¿Vale? However, I also need the slope, right? And so how can I get the slope from here? Well, again, from your formula booklet, you will discover that you have the, I think they call it the gradient formula. It's also in your formula booklet. Remember that the gradient is the same as slope. And the gradient formula, you should recognize it as m equals y2 minus y1 divided by x2 minus x1. So in this case, instead of needing 1 point, here you actually need 2 points. The moment, and here's the other big brain play you can sort of think, the moment that you have 2 points, that means you can get the slope. And so if you have 2 points and you get the slope, well, you can spend one of those points for plugging it over here and get a line. So what is this whole like logical implication giving you? Is that if you have 2 points, you can create a line. Because from these 2 points, you get the slope. And one of those points will be your point that you plug into the point slope formula. I just said point like 20 times in 2 seconds. That was pretty exciting. Anyways, so how do I get the slope from here? Well, you need to plug in those 2 points, ¿cierto? And you define which one is your first and which one is your second, see? And so intuitively, it makes more sense for this one on the left to be my first, just because it shows up first. So if this is x1, the 0, then that has to mean that this -1 is y1. In other words, this 2 has to be x2, and this 0 has to be y2, okay? As long as you're organized and plugging in, you're gonna get these points easily, see? So my slope, now like actually plugging in for part A, my slope has to be y2, which is 0, minus y1, which is -1, divided by x2, which is 2, minus x1, which is 0. So notice how I plugged it in parentheses, just so that I don't mess up the double negatives. So up top in the numerator, I end up with +1, and on the bottom I end up with 2. See? So the slope for my equation for part A is 1/2. See? Now, for part A, they're still asking for the equation of the perpendicular bisector. So I just found the slope. So ta-da! And now I need to find a point to plug into the point slope form. And I will be choosing to plug in this guy here. See? So boom, I have my point. Boom, I have my slope. I just need to plug in into the point slope formula. So let me give or make a little bit of space up here. So the point slope formula was y minus y1 equals m parentheses x minus x1. All right, cool. What did I discover? That m is 1/2, and that one of the points that I can plug in is 2, 0. And so if I plug everything into my point slope formula, I end up with y minus 0, because this is y1, this is x1, ¿cierto? y1 is 0, x1 is 2, equals my slope for m, 1/2, parentheses x minus 2. So y minus 0 is of course 0. This 1/2 is going to go ahead and distribute. So that means I end up with x divided by 2 minus 1/2 times -2. You can check with your calculator, but you should end up with -1. Okay? So here is my equation for the perpendicular bisector of BC. I don't know why I was writing A. So for part A, here it is. And if you don't trust me, well, it's about time that you do. Here it is. There's the -1, and here they put 0.5 times x, which is the same as saying 1/2 times x, which is the same as saying x divided by 2. So all of this is the same. You can put it as decimal, leave it as fraction, whatever you want. See? That is for part A. Then we discover, or actually not discover, but then they tell us, right, that for part B, the equation of the perpendicular bisector of AB is this. And so AB, which will now be putting in green, it's whatever is the perpendicular bisector between A and B. And so between A and B, it makes more sense that it's this guy here. ¿Cierto? So the equation of this guy is y equals -3x plus 23. And on the other hand, right, we have that the equation we just discovered for part A is that y equals -1/2 x minus 1. Sorry, +1/2 x minus 1. Talking about this guy here, by the way. See? Just going to rewrite it. Probably makes more sense to most of us if I leave it like this. See? It's the same thing. Yeah, so those are the two equations I have. That is the information that I have at hand. And for part B, you need to find the coordinates of point V. Point V, which I am now putting in red, is this guy here. So find the coordinates of point B where the perpendicular bisectors meet. Give your answer to, let's not forget that, to 4 significant figures. So you guys, think about it this way. They're telling us to find point V. And they tell us that point V is exactly where the perpendicular bisectors meet. So if it's where they meet, it's where they intersect. And here's the big brain play. If it's where they intersect, it's where they are equal to each other. Ladies and gentlemen, whenever two lines intersect each other, then that means those two lines at that point are equal to each other. And why would they be equal to each other? Because they would share the same x and y values. They share the same x and y values right where they intersect. And so that means that they have to be equal to each other. So think about it this way. If this is my line 1 and this is my line 2, and they tell me, yo, apparently they intersect, they are equal to each other, and find the coordinates of that. See? So you're going to go ahead and take line 1 and equal it to line 2, quite literally. And if you go ahead and take line 1 and equal it to line 2, then that means, well, think about it. How can you make them equal to each other? Well, they both have a y on this end, ¿cierto? So think about it this way. You can have like a y equals y, and I know this is kind of weird, but you can have a y equals y, ¿cierto? And this y is going to be from line 1, and this other y is going to be from line 2. And so the y from line 1 is this whole thing, negative 3x plus 23. And the y of line 2 is this whole thing, which is 1/2 x minus 1. And although this looks kind of weird and kind of nasty, think about it. How many variables do you have right here? You only have x. Yes, there's one on the right. Yes, there's one on the left. But from here, you can find x equals something. Okay? But the more important big brain play that I really need you to understand for the day of the test is that when lines meet or when they intersect, they are equal to each other. So go ahead and equal those lines. That's all you gotta do. All right, let's get to it. So from here, you gotta get x, ¿cierto? So throw everything to one side, then everything to the other side, and see what happens. So in this context, I'm gonna choose to have all my x's on the right side. So that means I gotta do, for example, I don't know, plus 3x to both sides. So that means I end up with 23 equals 3x plus 1/2 x is going to give me 3.5x minus 1. And from here you want to get x alone, so you go ahead and do plus 1 to both sides. That means you end up with 24 equals 3.5x. So from here you want to solve for x, divide both sides by 3.5 in order to get x alone. So x has to equal 24 divided by 3.5. Now, I need to go get my calculator, so give me a second. So from here, we can go ahead and do 24 divided by 3.5. 24 divided by 3.5 will be giving me that. So x equals 6.857. 142. Now, from here, right, I just found the x value, ¿cierto? So the x value that I just found for point V is exactly that. It's 6.857 blah, 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 ¿cierto? Now, if you want to find your value for y, all you have to do, because they intersect here, is that you got to take that x value, ¿cierto? And plug it in either in line 2 or in line 1. And they will both give you the corresponding y value, okay? Because they meet here, they both have to give you that answer, ¿cierto? So I'm going to go ahead and plug it in. I don't think it really matters. I'll plug it into line 1, see? So if I plug it into line 1, that means I have negative 3 times my value of x, which is this guy here, ¿cierto? Close parentheses, plus 23. And so from there, your value for y has to be 2.42, 8571. $8571.4, ¿cierto? All right. Now, we're almost done here. See, the last little bit of challenge that is missing for part B is that we need to give our answer to 4 significant figures. So guys, for 4 significant figures, all you have to do is the following. Write out the entire number as is, and you will count 1, 2, 3, 4, and on your 4th number, because in this case 4 significant figures, look at the number to its right and see if you round it up or keep it the same. In this case, the number to the right is not 5 or above, it's 4 or below, and so we actually keep it the same. So for 4 significant figures, for x, we're going to leave it as 6.857. Okay? That is a very weird 8. Let me draw it again. There we go. See? Well, for y, we do the same thing. We count 1, 2, 3, 4. Do we round it up or keep it the same? You round it up because right next to it you have a 5. So you're going to go ahead and round it up, and you end up with y equals 2.429. And if we go ahead and check our answers, let's hope I'm right. It looks to me like I'm right. So right here, the 6.857 and the 2.429 are right over here. See? So that is my value for x, that is my value for y. Technically, these are the coordinates of point V. If you want to do like the mega final answer and get really fancy, I'm pretty sure this gives you full credit, but anyways, technically the coordinates for point V would be to write it out as is, ¿cierto? So you should be doing something a little bit like that, see? All right, there we go. So that would be for part B. And last but not least, the weirdest part, mainly because it has to do with understanding how a Voronoi diagram works, has to do with the following, ¿cierto? So they tell us that a Voronoi diagram is constructed with points A, B, and C as the 3 sites. And we need to draw, for part C clearly, the edges of the Voronoi diagram on the given diagram. So what the heck even is a Voronoi diagram? Guys, this is actually a very cool exercise because it forces you to really understand how a Voronoi diagram works. And I think it's worth listening to the monologue you're about here because it's going to help you also understand why perpendicular bisectors are a thing within the world of Voronoi diagrams. So, when do people use Voronoi diagrams in real life? They might use it for, like, I don't know, building schools, okay? Because you don't want to have like one region filled with 10 schools and the one right next to it filled with 2 schools. You want them to be spread out evenly. You want them to be spread out evenly. You want the space between them to be equal to each other, okay? And so a lot of times for like building cities and stuff like that, a Voronoi diagram would make like a lot of sense, ¿cierto? So it's mainly used for spacing and stuff like that. So imagine points A, B, and C are all like schools, right? And maybe this is whatever, like kilometers, right? And so you're trying to see where to put the schools, and someone defined, it has to be at sites A, B, and C, ¿cierto? And sort of like the proof that happens from there is the perpendicular bisectors that arise from those sites, ¿cierto? So you define the sites, then you define the perpendicular bisectors, and voila, there you have your Voronoi diagram basically. See? Point is, here you have a bunch of lines, ¿cierto? And so they tell you to draw clearly the edges of the Voronoi diagram. And so there's a couple right answers, a couple wrong answers. I mean, there's one right answer, ¿cierto? But what a lot of people would maybe eyeball and get wrong is if they say like, oh, okay, so the edges of my Voronoi diagram are maybe like this, and then like that, and then like this. See? And they don't really know why. ¿Cierto? They just kind of eyeball it, they go with it. And that is what I mean, that listening to this monologue will help you understand what is the right way to do it. ¿Cierto? So this is the wrong way to do it because you're kind of like eyeballing it. ¿Cierto? The thing is, even if I were to draw in the bisectors that I mentioned, so the bisector AB is this, the bisector AC is this, ¿cierto? And the bisector BC is this, you can't draw all of it in because a Voronoi diagram has to be split up evenly, and this wouldn't be even, ¿cierto? In fact, this might be even if I have like a point D over here, but I don't, ¿cierto? all this space here is kind of like left there lying in space. It doesn't make sense. And so what does make sense? See, let's get to the point. What would make sense, ¿cierto? Or actually, I think it's better to understand that what doesn't make sense, ¿cierto? If I include this line here, ¿cierto? Here's the thing. If I include that line right there, if I were to include this line as an edge, you have to ask yourself immediately, okay, this is pretty much a line that is gonna be an edge between A and B, ¿cierto? And so if this is the edge between A and B, is the distance from here to here same as the distance from here to here? Clearly it's not, ¿cierto? Is the distance from, I don't know, like here to here same as from here to here? Not really, right? You're off by a little bit. And so that is how you have to like imagine it or think about it, ¿cierto? You could prove it mathematically, but for part C, you can just eyeball it. See, they don't ask you to prove it. And so from here, ¿cierto? So this is the bisector between A and B, ¿cierto? And if I include this entire line as an edge, it partly makes sense because from here to here is the same as from here to here. And notice, even counting like these red dotted lines, you can sort of see that it's 3 squares. And from here to there, it's also going to be 3 squares. And so that is a way in which you can actually eyeball or make an educated guess, ¿cierto? So that is an edge that we have to include, the one that is up here, ¿cierto? That is an edge that we have to include, but do we have to include the edge that's down there, ¿cierto? The edge that's down here doesn't make too much sense because from here to here, is it the same from there to there? Nuh-uh. And so in this scenario, the edge we have to choose for the bottom so that A and C are at a similar length is actually this edge right there. And here we can do the same sort of like logical, like maybe approach if we want to think about it, ¿cierto? From here to here, ¿cierto? It's pretty close from there to there. If you calculate that distance, it will be equal to each other, ¿cierto? Eyeballing in this scenario is a little bit harder, but I think the explanation of how it works is much more important, ¿cierto? So that would be your other edge. And your last edge, ¿cierto? Would have to be between this and this, ¿cierto? So notice, this guy on the top left is the perpendicular bisector of AB. This guy on the right is the perpendicular bisector of BC, and this guy on the bottom is part of the perpendicular bisector of AC. What's important when you pick your edges is that you pick, like for example, the entire perpendicular bisector of AC is this entire line, but I only picked as an edge half of it. And the same for BC. The perpendicular bisector of BC is this entire line, but the edge will only be half of it. Okay? So, again, this is sort of like an eyeballing thing. What I suggest though is that you redraw those perpendicular bisectors and you keep in mind you usually only keep half of it, ¿cierto? If you keep the whole line, it's not gonna work like entirely, ¿cierto? So only take the half that for you helps. See? Again, the perpendicular bisector of AB is very, very useful for this part here, but you don't need the perpendicular bisector for AB down there. You don't care about the part down here, so don't include it as your edge. See? Okay, I think near the end I was a little bit more clear on how the edges work. It's a little bit hard to explain, but I tried my best. And also, this is a very, very particular question for the AB. I don't usually see that they ask you to draw the edges of a Voronoi diagram, but today they did. See? So ladies and gentlemen, that is for number 6. And just so you believe me, there's the answer as well.